We're Team L3G22, better known as Team B-Dazzled-Blue, and this is our code review for the SYSC4805 Computer Systems Design Lab. I'm going to hand it over to Joseph.
Hey, I'm Joseph. So as a little reminder, the goal of this project was to create an Arduino-powered robot that could clear a perimeter of snow blocks while avoiding obstacles under a 5-minute time limit. We're going to quickly walk you through our project's repository. It's split into three parts, each with their own subdivision. The docs folder contains copies of all our reports. The source folder contains subfolders of code used for programming our robots, and the test folder contains tests for our different components. Now we're going to take a look at the line follower code. So the line follower code logic displayed here. So you can see we have three defines for the line follower sensor, left, middle, and right. Since there's three sensors, we use the analog A5, A6, and A7. We have a threshold value, which is basically the value that our sensors will scan. And if it's over this value, that means we detect a black line. If it's under, we're okay. In the setup, we have the pin mode, which basically just sets the left, middle, and right sensor all as inputs. Then in our loop function, we basically just constantly loop this and we keep scanning our values for the left, middle, and right sensor. Then we check the left, middle, and right to check, like I said before, if it's above the threshold, which means we have a black line. And if so, then we want to redirect the robot. So we basically stop, delay, reverse, delay, stop, delay, and do a random turn. And once we are good, it'll then go to the else, which it'll move forward. Now I'm going to pass it off to Danya to do motors and ultrasonic sensors.
Hi, my name is Dani Mahmoud, and I'm going to start off talking about ultrasonic sensors. This file essentially implements the obstacle detection logic using two ultrasonic sensors hooked up at the front left and front right of the robot chassis. So how it works is that it measures the left-hand side and right-hand side ultrasonic sensors' distance to any possible obstacle up ahead by sending a trigger pulse, and then measuring the time it takes for the echo reply to return and converting that time into distance. This distance is then compared with a 15 centimeter threshold as shown, and if the distance between the response received measured to be 15 centimeters, the robot will stop, reverse, and then randomly turn and continue. Now we can head over to the motor code. This file includes all the basic motor functions that are used in essentially all the other codes. Basically, the most important function here is the random turn because this is a function that will be invoked every time the robot reverses, and it will turn the robot between 90 degrees and 180 degrees randomly. This ensures that we avoid the robot getting stuck in circling the same corner or other edge cases.
Okay, and from here, what we're going to do quickly is we're going to go over to our tests, and we're going to go over our watchdog timer test. What this program does is that it's a simple watchdog timer for the Arduino do with two unit tests. First, we define three watchdog functions. Watchdog enable, which configures the hardware watchdog with a 4-second timeout. So if the code doesn't work in time, the microcontroller auto resets. We have watchdog reset, which restarts the watchdog countdown, and watchdog setup, which is an empty placeholder. So our first unit test will go all the way down here. What is happening is we're running three fake tasks, and after each task, we call the watchdog reset. So as long as the program keeps feeding the watchdog timer within 4 seconds, the system runs for 15 seconds without resetting. And then in our second unit test, we're simulating hanging with an infinite loop that never calls watchdog reset. So after about 4 seconds, the watchdog timer times out and the resets the whole board. So all of this helps us to test that our system can automatically reset whenever there's a freeze or a hang or it gets stuck.
For the motor speed test code, the code is designed to measure our motor speed changes with different PWM value. It's run the motor at 9 predefined PWM levels, keep them running for exactly 2 seconds, and then ask the user to input the measured travel distance. After each test, the code calculates the speed, print a summary, and log whether the result passes a speed threshold. The motor direction test let us control the robot use simple keyboard command like WSAD. Each command trigger a movement like forward, reverse, spin left, spin right, and the code run the action for set duration before automatically stop the motor. It also allows the user to change the default speed and time. For the lens sensor test code, the code is just to check how well our front sensor can tell black from white. The program reads the raw analog value from all three sensors, compare them to threshold, and show whether each one detects correctly. It also keeps tracking of states like how many tests we run, the overall accuracy, and any false detection. The ultrasonic sensor code we mainly test two things: distance, accuracy, and the card reaction time. For accuracy, the code measure object at like 10, 20, 30 centimeter, takes some readings, and then calculate the average and error. And for the reaction time, the card actually move forward while both sensors are active, and we measure how quickly it detect an obstacle and stop.
Hi, my name is Sabesha, and I'm going to explain how we used free ATAs on the Arduino Uno for our project. At the top of the code, we have include the free ATAs and motor driver libraries. Then we define all the pins for the line following sensor and the two ultrasonic sensor and the 4 motors. We also define 2 structs to store our sensor data, one for the line following sensor and one for the ultrasound distance sensor. And these are shared across multiple tasks. Next, we set up the watchdog configuration. The watchdog is set for a 4-second timeout for each, and as each task is assigned a bit mask. Every task sets its own bit when it runs successfully, and the watchdog checks it later to make sure nothing has crashed. In the watchdog enable, we set up the hardware part of the watchdog timer, and in the watchdog reset, we refresh it. Then we have to create queues for the motor commands. Here we have the helper functions for the motor drivers and the various functions that would set the motor speed and directions it's moving in. Then we move on to a sensor task. The line follower sensor task, 3-channel IR line follower sensor for 50 milliseconds and sets a flag if it detects a boundary line. Each ultrasonic sensor sends a trigger pulse, measures the echo return time and converts it to distance and marks whether an object is detected. And at the end of each loop, all tasks check in with the watchdog by setting their bit. And the watchdog itself runs once per second. It compares all the task check-ins against the required mask. If every task has reported in, we reset the watchdog. If not, we print out which task is missing. This helps us detect freeze or timing issues during debugging. Next, we have the motor control command task. Instead of letting every task control the motors, we send all the movements through a free ATAS queue. The motor control task reads from that queue and then performs actual motor actions. This prevents conflicting commands and keeps motors centralized. Then we have the command task, which acts as the robot's decision maker. It checks the shared sensor data and decides how the robot should move. If the line follower detects the boundary, we stop, reverse, and randomly turn. If either ultrasonic sensor detects an obstacle, we do the same avoidance. Otherwise, we send a forward command, and just like the other task, it checks in with the watchdog timer at the end of each loop. Finally, we have the setup function. We create our queue and start all 6 tasks with their assigned priorities. Once the free ATAS scheduler starts, all the tasks run in parallel, and the robot operates autonomously with real-time sensing, movement, and watchdog monitoring.